Hey, what's up, guys? This is Chung here again. So this time, number 1872, Stone Game 8, I believe. Wow, a lot of Stone games. Okay, so this time Alice and Bob playing another Stone game, and so this time the rule is like this. So there we have n stones in a row, right? On each player's turn, uh, while the number of stones is more than one, right? And then the player can do the following. Basically, he can choose uh, at least two stones from left to pick, and then of course this person will get the scores, right, for those stones. And after that, the third step is basically after that this player will place a new stone uh, equals to that to the sum of the value of the stones he just took on the left of the on the left side of the row, and the game stops when only one stone is left, right? Okay, so now as usual, right? So this is a game theory problem. Basically, we want to maximize the score difference for Alice, right? And Bob will just will try to minimize Alice's score, which also means Bob is also going to maximize his score, right? Basically, each player will try to maximize his own score. That's why it's called both player will play optimally, right? So and then we have some examples, right? So and there's like the stones here. So each stone will have like different values. Some stone will have like negative values here. So output is 5 because uh, the optimal solution uh, Alice can take, right? Since Alice will move first, is to take the first four stones, right? And then basically we have 1 minus 1, 2, 3, minus 3, 4, and minus 5. So I think Alice basically he will take these 4 stones first, right? So and whose sum is like is 2, right? And after that, based on the rules number 3 here, we need to put the sum in back into the into this kind of array. So now we have a 2 and a minus 5, right? So in this, when there's a obviously when there are like only 2 stones left, the other person does not have any choice but to take all of them, right? Which means so Alice will have 2, right? And then Bob will just take the remaining 2, which is have minus 3, right? That's why 2 minus 3 is 5. Because after taking 2 here, right? Taking the last 2 will put minus 3 back into array. But based on the description, the game stops when there's only one number left. Basically, the game stops when there's only 2 numbers left, right? Because the last person will take both of them. That's how we get 5, right? And then this one is similar. So, and yeah, like I said, so this is like basically the base case, right? When there are only like 2 stones left, there's only one option, right? Just to take both of them. So the constraints is like this, right? 10 to the power of 5, and here's the stones range here, similar to the n here. I mean, every time for this kind of stone game, most likely it's gonna be a DP solution. But if you try to solve this one with a naive DP solution, which is the every time, let's say we have a DPI here, right? We have DPI, and then I means that starting from I, uh, what is the maximum score? What is the maximum gain, right? Maximum difference I can get starting from I. So the naive solution will be starting from I. Basically, we'll try all the possible j, right? We'll try all the j between I and j to n minus 1, something like this, right? And then we'll try all of them, and then we'll get the maximum value of this one. That's going to be a naive approach. Obviously, this one is going to be an n square time complexity, right? Because for each one, we're going to try everything starting between this range. And that will TLE given this kind of range here, right? So which means we need a better solution, right? And that's why this one is a hard problem, right? So basically the tricky part is that this one, I don't know if you can call it a greedy or something, but instead instead of trying all the possible J's here, what we can do is like this, let's say we have a DPI, right? So for DPI here, basically we're sitting on the ith number, right? So let's say we have, let's do this 1, 2, 3, 4, 5, 6, right? So let's say we're sitting on this 2 here, right? So we are on I here, and and I think first thing we gotta be clear is that whenever you're sitting on this I here, this current number, the number right here is what? It's equal to the presum of this array here, because for the presum we have 1, 3, 6, 10, 15, and 21. Because every time after we took some numbers, we'll put a one number back, right, as with the same value as the sum. So which means that whenever we are at like index I here, which means that the first 0 to I minus 1 stone has already been taken. In that case, actually this 0 to I has already been taken, and which means that the value of this I here will be the presum. Which means let's say for example here, the first two stone has already been taken, right? And then that's why we have 3 here. So similar for if I is pointing to here, it means that the first 3 stone had already been taken away, and then after that we'll add like 6 back. Okay. All right. So let's assuming we're at like index I here. So it means that the first I 0 and I stone has already been taken away, and after that we'll put like another number back here. That's why we're pointing at 3 here, right? And so if we look at the DPI here, we don't necessarily have to try all the possible ones here, because actually we only have like 2 options here. So the option is that we either take basically we either take this 3 so basically we either take the next 2 numbers or we don't take, right? Starting from here, right? And actually, the way we're doing this DP here is we're gonna do it from the end, because we'll be needing the DP value from the end, because the DP n minus 2 is fixed, right? So which means that for the last 2 numbers, it's we have to take everything basically. This DP n minus 2 will equal to the what? To the presum of minus 1. Because when we take the last 2 values, right, it means that it means that we're taking everything from this array here. Because when there are like only 2 numbers left, so what's gonna be those 2 numbers? It's gonna be 15 and 6, right? Because for 15 is the presum of the previous value numbers, and plus not the next one. And if we take these two, it's what? It's 21, right? So 21 is exactly the same as the presum, the last presum. Okay, okay. So back to the DP here. So if we calculate DP from the end, right? It means that we already have like a base case, which is DP n minus 1. And now when we add like DPI here, so like I said, we have 2 options here. We either take the next 2 one, or we don't take it. We don't take it means that we're gonna try to take the next 3 one, or the next 4. Okay. And so let's say the first case. So the first case is, let's say we take the first 2 we take the first two numbers. Sorry, not the next two numbers. So what's going to be that? So the values we're getting is what? We're getting is the presum I plus 1. So this is the first scenario, which means that we're starting from I here, if we take this two, this two here, so what's going to be the number we're getting here? It's 6, right? Because 3 plus 3 is 6. That's why, the number of the value, the score we're getting by taking the next two number is like this. It's the presum I plus 1. And after this, what's going to be basically after taking the two numbers, basically we're handing this game to the next person, right? And the next person will also play optimally, right? Which is also like what? It's going to be a minus dp I plus 1, right? Because after taking the next two numbers, which is 6, right? And so first we're getting this presum here, right? And how about dp I minus 1? Why this dp I minus 1? Because after taking this 2 3 away here, we're going to put 6 back, right? And this is I plus 1. So which means that if we take the two numbers, 2 and 3 here, the next two numbers here, basically the next turn is the next person. So the next person will also play optimally, which is this dp I plus 1, because the next person now is at this I plus 1 position because we have a 6 added back here, right? So that's the first scenario here, right? And how about the second one? So the second one is like this. So basically, we only have like the second one is that we'll try to pick 2 3 4 and 2 3 5, so on and so forth, right? Let's say if there are like more numbers down the road here. So for those scenarios, actually, we don't have to try out all of them, because the reason being is that because it's just the same as the dp I plus 1. Right? Because starting from 2 3 4, let's say starting from here. Starting from here is what? Actually, this one is the same as the dp I plus 1. I know this is a little bit tricky here. Let me try to explain a little bit more here. So this part is really important. That's the key to solve this problem. 7, 8, 9, 10, right? So let's say we have, this is a 1, I think 3, 6, 10, 15, 21, 28, right? And then what? 36. Is that 36? Okay, 36. Yeah, and then it's 45, and then 55, right? Something like this. So we're at this I here, right? So this is I. So the first scenario is that we take next two stones, right? And this one is what? This is a presum I plus 1, right? Because the next stone stop at here. Stop at here. And the value we're getting is the presum I minus 1 and minus the dp of I plus 1, right? Like I said, after taking the two stones, basically we're handling the game to the next person. So next person will start from I plus 1 here, right? Because we're adding, again, we'll always add like a stone back, okay? And the second one is like this, right? We take next 3 stones, right? Next 3, 4, 5, so on and so forth, right? So that's the second scenario. So for all this kind of 3, 4, 5, actually, we're gonna get what? Since remember the purpose of us is to get the maximum difference, right? So actually this one is like a sub problems, right? As you guys can see, because the 4, 3, 5, 6, 7, or whatever it is. Actually, this one is what? It's a DP I plus 1. It's the DP I plus 1 here, right? I mean, because if we take the next 3 here, actually it's the the next 3 here is exactly the same as DP I plus 1 here. Because DP I plus 1 means what? It means that we're standing at I plus 1, right? And we're trying to maximize our difference. That's exactly the DP. That's exactly the next 3 number means, because for next 3 numbers it's like this one, right? And the next 3 number is the same as the DP I plus 1, because again, right? So since we're going to accumulate all this number here, for the next 3 numbers, for DP I plus 1, we'll have what? We'll have 10 here. We'll have 10 be replaced here, and then 5. Right, so basically, as you guys can see, so we have 6. Basically the next 2 numbers, it's 6, 4, and 5, right? And the next 3 numbers is like 10 and 5. So these two are identical. In a way that in the DP way, basically. So I know I'm repeating myself. I'm just trying to make things clear to you guys. Sorry about that. So again, right? So next 3, 4, 5. It doesn't really matter how many of them, but because we're getting the maximum among all of them, right? And the maximum among all of them is the same as DPI plus 1. Because remember, DPI plus 1 means that it's the maximum difference we can get starting from I plus 1, which is exactly the next 3 numbers here, right? Because the next 3 numbers here is the same as the DPI plus 1 is the next 2 numbers, right? So then, as you guys can see now, actually I don't have to try next 3, next 4, next 5, so on and so forth. All we need is this kind of DP value here of I plus 1, because this one will tell us starting from I plus 1, right? What are the maximum difference I can get, right? And I just need to choose the better one from these 2 scenario here. And yeah, so that's it. And I guess we can start coding then, right? Actually, once you figure that out, the coding is extremely short, to be honest. So first, we need a presum, right? Presum is gonna be, I'm gonna use Python's accumulate, right? Accumulate of stones, right? It's a shortcut to accumulate and then convert it to a presum to calculate the presum here. And I have n equals to the length of the stones, right? And I have dp, right? So if I define dp here, at the beginning, it means that the maximum value we can get starting from this index. At the beginning, it's like the max is a negative, biggest negative value, right? And then, like I said, the dp n minus 2, right, is what? It's a presum of n minus 1, right? Because if we have 2 value left, we have to take both of them. And if we take all the stones from, if we take both of them, the total sum is the same as the presum. Okay. And then, like I said, we start from the end, which is going to be the n minus 3, right? Because we already figured out the n minus 2 here. And then we start and then we just do this -1 and -1, right? So basically, so we have two options, right? The DPI is like the first option is what we take the next two numbers, the next two numbers. So by taking the next two numbers, we have presum of I plus 1, right? And then after that, we're handing the game to the next person, and the next person basically will play optimally, which means that he will try to get like the maximum difference starting from the DP I plus 1, right? And next one is that if we don't play, I'm sorry, if we take if we try to take the next 3, 4, 5, and 6, in that case, actually it's exactly the same as the DP I plus 1. And in the end, we simply return the DP0 here, right? So that's it, right? I mean, that's the code here, right? So as you guys can see, this is pretty fast because the time complexity for this one obviously is like O of n. Actually, as you guys can see, since we're only depending on this DPI plus 1 here, we can just reduce the space complexity to what? To O of 1. Actually, and yeah, but yeah, you can say here is like already like O of n space complexity. But if we just utilize update the stones here, we can think this one is like O of 1 space complexity. But let's try to do this, right? So basically, we have a DP here, and so all we need actually is a DP, right? We just need a DP value here, and then every time we just update DP, right? So we can just remove this one actually, right? This one as well, and this one as well. So in the end, we just return the DP. That's gonna be the final answer. I believe this should also work. Yeah, right. Yeah, so I think that's it, right? I mean, I'm gonna give this one back because I think this one is a little bit easier to understand. I mean, this one is pretty straightforward, right? I think no, it's kind of straightforward because if we take the next two, the value we're getting is like a presum I plus 1 here. This one is a little bit tricky. Basically, this one covers all the scenarios that starting from the next three and next four, next five, because that's exactly the definition of this one, right? We're getting the maximum one. And yeah, so that's it. It's very, very, very cool problem. The thinking process is pretty tricky, but once you figure it out, look at how short the code is, right? It's pretty amazing. And with that being said, I guess I'll just stop here. Okay. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.